Okay, good afternoon, everyone, and welcome back to day 2 of our course on difference in differences, organized by LISER in collaboration with the Doctoral School in Economics and Finance and Management of Luxembourg, University of Luxembourg. We are very happy to have once again Professor Clément de Chaisemartin as our guide for this journey in the world of difference in differences. Before we begin, I will make again a quick reminder. These sessions are being recorded and will be available on the LISER's website and YouTube channel of LISER. If you don't want to appear in the video, please turn off your camera and don't use the chat. Our next sessions will take place in LISER and online, so will be hybrid, and will be on Tuesday, the 1st, next Tuesday the 1st, full day, and then we'll continue on Wednesday the 2nd until midday. Then we will have an hybrid seminar. If you want to participate in the seminar, you have to register. I will put again here the link for registrations. And as last time, if you have questions, feel free to write in the comment chat, and then LISER's team will filter and forward it to Professor Clément de Chaisemartin. So note that for the next 2 days of the course, questions will be taken only from in-person participants, not from online participants. But you're very welcome to join us in person at LISER if you wish to do so. Just let us know. So that's all from me. Professor Clément de Chaisemartin, the floor is yours. I think we can start.
Okay, perfect. Thanks everyone for being here today. So we're going to continue the class. So we last time we had talked about we had laid out the setup and our main assumptions, and we had started discussing the quote-unquote classical Diff-in-diff designs, where we have a binary treatment that's absorbing, meaning that once units are treated, they cannot opt out of treatment, and we don't have variation in treatment timing. Okay, and in that setting, we had discussed static two-way fixed effect estimators, where you regress the outcome of group G at time t on group fixed effects, time fixed effects, and the treatment. And we had seen that the treatment coefficient in that regression under a parallel trends assumption and a no anticipation assumption is unbiased for the average treatment effect on the treated. But then we had discussed the fact that sometimes researchers might want to estimate more disaggregated effects, these ATTL effects, which measure the average effect of the treatment of having been exposed to the treatment for L periods. And we saw that to estimate those ATTL effects, researchers may use those two-way fixed effect event study regression that I'm showing now in the class notes in equation 3.6, where we regress YGT on an indicator for the treatment groups, a set of time fixed effects, and those relative time to treatment indicators that are equal to 1 if GT is such that a group is treated and has been treated for L periods. And we had seen that those event study regression coefficients, they can actually be expressed as simple diffs in diffs, comparing the outcome evolution from the period just before treatment to L periods after treatment across the treated and the control groups. So last time we saw that for positive values of L, namely for relative time indicators for after treatment, under our no anticipation and parallel trends assumption, those event study estimators are unbiased for the target parameters ATTL. But now the event study, two-way fixed effect event study regression can be used to estimate the event study function that maps L into ATTL. Now this regression can also be used for a different purpose. So the result that I'm stating now is that for negative values of L, we have that under the no anticipation and parallel trends assumption, the expectation of beta at FEL is equal to 0. So first, let's prove this result. To prove the result, we use the formulation of beta at FEL as a simple Diff-in-diff, and then we use the fact that the design is conditioned upon and the linearity of the expectation to move the expectation from outside to inside the summations. And then we use the fact that we are in a classical Diff-in-diff design, and therefore, because L is negative, we are always looking at outcomes before period F, and before period F, we know that nobody, be it in the treatment group or in the control group, is treated, and therefore the outcomes we observe are actually potential outcomes without having ever been treated. And finally, by the parallel trends assumption, we know that the treated and the control groups in expectation have the same evolution of their never treated outcomes. So that's why these two terms cancel each other out and we get a 0. So now I have a question for you that you may want to reply to in the chat, which is as follows. So how can, based on this theorem, how can we test the no anticipation and parallel trends assumptions? Yeah, exactly. Yeah, exactly. So Anna, Beatrix, and Matteo. Yeah, exactly. So all of those are correct answers. So what this result is showing is that assumptions, no anticipation, and parallel trend have a testable implication. Okay, so what does that mean? What that means is that if we have no anticipation and parallel trends, then we have that the expectation of those coefficients is equal to 0. So it's a testable implication, but we don't have an if and only if, because we don't have that if this is equal to 0, then assumptions, no anticipation and parallel trends hold. Okay. So that means that those assumptions are, we say that they are refutable, they can be proven wrong, but they are not fully testable. Okay, so another way of saying that is that we say they are partly testable. They have a testable implication. So now, like all of you in the chat said, a way to implement the test will indeed be to check if those coefficients, event study coefficients for negative values of L, which we are from now on going to call pre-trends coefficients, we're going to check if those pre-trends coefficients are significantly different from 0 or not. Okay, so now that leads me to the next question. So let's assume, which actually someone already answered, let's assume that F is greater than 4. So that means that treated groups start getting treated at least at period 4 or even at a later period. But if it's at least at period 4, that means that we can actually compute two pre-trends coefficients. Okay. One that's going to compare the outcome evolution of the treated and the controls from period 3 to 2, and another one that's going to compare their outcome evolutions from period 3 to period 1. So that means that the null hypothesis that all of those coefficients has to be 0 is going to be a vector of dimension strictly greater than 1. So then, would it be correct to test separately that all of the coefficients are 0 and reject the null hypothesis of parallel trends and no anticipation whenever we have at least one t-stat attached to those coefficients that's, say, greater than 196 in absolute value? And if this testing procedure is not a correct testing procedure, what's the issue with it? Yeah, exactly, Andrea. So the problem is that this would give rise to a multiple testing problem. Okay, we are testing simultaneously many hypotheses without accounting for it. And so, as someone already said in the chat, to do pre-trends test correctly, you have two options. The first one is to it does not really interact with the conditioning on the design, but we can talk about it when I mean LISER. So we can run an F test then that all of the coefficients are equal to 0, or we can adjust directly p-values for multiple testing, doing a Bonferroni adjustment, or following this other paper that I'm describing here, which proposes an adjustment related to Bonferroni, but that's going to lead greater power. So, but between these two family of tests for pre-trends, F-test or some kind of Bonferroni adjustment, you're going to have that both tests are valid, and they give you asymptotically a nominal size under the null, but neither test dominates the other in terms of power. So essentially, this F-test here is going to be more powerful than the other if you have that all of the pre-trends are a bit different from 0, but none of them is extremely different from 0, while this other test here, which amounts to looking at the largest pre-trend estimator, will be more powerful if the violation of pre-trends of no anticipation and parallel trends are such that you have one pre-trend coefficient that's very large, while all the others are close to 0. Yeah. But so typically, so in terms of their statistical properties, there is no strong reason to prefer the F-test over the test based on the maximum of the pre-trends estimator. A bad reason to recommend the F-test is just that the F-test is implemented in, essentially all statistical routines that you can think of. So just out of convenience, and that one is a bit easier to implement. Okay, so then another interesting question that we believe has received barely any attention and more research is needed actually in that direction is how many pre-trend estimators you should show. Because sometimes, not always, but sometimes F is going to be very large. So you have data for many, many periods prior to the beginning of the treatment. And so then in that case, you could theoretically compute very, very many pre-trends estimators, and then you could be testing whether treated and control units were experiencing parallel trends for a very long period of time. And so in that case, you may find that for the 10 years prior to treatment, the treated and control were experiencing, roughly speaking, the same trends, but beyond 10 years, trends start being noticeably different between the two groups. And then the question is this a concern or not? Or in other words, how many insignificant pre-trends should you be able to show to convincingly demonstrate that you have a parallel trend? So there is no paper that has tried to, give a nicely formalized answer to this question. So what I'm going to give you is really just a common sense cooking recipe at this stage, calling for more research on this. Which is that the number of pre-trend estimators you show should be commensurate to the number of event study estimators you show. Essentially, that if you're going to show, if your data is such that you can only compute 3 pre-trend estimators, then it's probably not a very good idea to show many more than 3 event study estimators. And the rationale for this recommendation is very simple, that your event study estimator of the effect of L periods of exposure is going to rely on a parallel trend assumption from f-1 to f-1 plus L, namely over L periods. And so if you want to back out, if you want to give some empirical support to this identifying assumption, you need to be able to show that for L periods prior to treatment, the treated and the controls were experiencing a parallel trend. And so if people, because we see many examples of that, if people want to compute many more event study than pre-trend estimators, then at the very least, they should acknowledge that their very long-run treatment effects, they are not able to empirically demonstrate the validity of the parallel trend assumption over such a long horizon. And readers and the reviewers of those papers should also discount the plausibility of those very long-run treatment effects estimated. Okay, so we're going to return to maybe I'll take the questions on the chat a bit together at the end. So we'll return to the question of event study estimators and pre-trend estimators a bit later. But for now, I'm going to ask you to use the data set and to actually estimate an event study regression. The outcome is always the patterns, and you're going to have one fixed effect for the treatment group. You're going to have year fixed effects and indicators for having been exposed to treatment for 1 all the way to 21 years, and 18 pre-trend estimators. Okay. And so I'd like you to tell me if, according to this regression, do we see that compulsory licensing seems to have an effect on US innovation? And then based on the pre-trend estimators, does it seem that the no anticipation and parallel trend assumption seem to hold? So when you look at the regression coefficients, does it look like compulsory licensing has an effect on US innovation? So up here, I'm going to be running the regression. And so and here I have this code to actually put all those effects on a graph, which is going to be a bit easier to read. Okay, and so you see those are the event study coefficients. And so you see that, so on the right-hand side of the graph, to the right of 0, we have the event study estimators, and to the left, we have the pre-trend estimators. And you see that in the long run, at least, starting a little bit 8 years after the treatment, but even more strongly 14 years after the treatment, we start actually seeing very, very large event study estimators that suggest that in the long run, having been granted having been given access to these German patents for free, actually had a positive effect on domestic innovation. Now, turning to the pre-trend estimators, so we see that first, they are pretty small, especially when compared to the very large estimated long-run effects. And, with a few exceptions, they tend to be individually insignificant. But to assess if jointly they are or not insignificant, we run an F-test, and here you actually see that at any conventional level, we reject the null of parallel trends. So even despite the fact that we seem to have some violation of non-anticipation and parallel trends, I would argue, and I think many people would agree with that pre-trends are unlikely to be a very big concern in this application, because even if pre-trends exist, their magnitude seems really much smaller than that of the estimated effects, okay? Which is something, an idea that we're going to formalize a little bit more soon. Okay, and the reason why actually effects take, at least 8 years to appear is that first, it takes time to patent an idea. So what Moser and Buena explain in their paper is that you apply for a patent and then you get it 2 or 3 years after application. So mechanically, you already have a 2-3 years lag between any effect of the treatment and the moment you start seeing this treatment effect materialized in the number of patents. But on top of that, it also takes time, to understand and acquire this new knowledge that you get access to after seeing those German patents and innovating from that. So that could explain why in total, assuming that innovation takes 5 years and the patenting process takes 3 years, that could explain why we only see effects arising after 8 years. Yes, so we're gonna. There was a question in the chat, but that's exactly what we're gonna be discussing soon, actually. Okay, and last thing is that so there are a few. Sometimes, in the book, we're not necessarily proving all the statements saying that such and such coefficient is actually a simple Diff-in-diff. So if you have doubts about this type of claims, you can always verify them manually which I'm going to do here. So I said that these event study coefficients, they are simple diffs-in-diffs comparing the outcome evolution of the treated and control from the year just before treatment, which in my case is 1918, to f-1 plus L. And so here we're going to verify the equivalence with diffs-in-diffs for the L is equal to 1 coefficient. So we want to show that, so the goal is to verify that that this coefficient here, which is 0.0235202, this beta at 1 coefficient, is numerically equivalent to a diff-in-diff that's comparing the evolution of patents from 1918 to 1919 in the treatment and in the control group. And so to do that, I'm going to compute my diff-in-diff manually by computing the average number of patents in the treatment group after treatment, the average number of patents in the treatment group before treatment, in the control group after, in the control group before. And then I will take my 2 diff-in-diff. And when I do that, I get exactly the same number as the regression coefficient. Okay, so the book and this course are a bit biased towards estimation and identification rather than inference, but it's still important to discuss a little bit, confidence intervals and hypothesis testing, and that's what we are going to do now. So the first thing is that to estimate the variance of these event study coefficients, it's actually pretty straightforward. We just need to compute the variance. So remember, those are diffs-in-diffs that compare the average f-1 to f-1 plus L outcome evolution in the treatment and in the control group. So to estimate the variance of the first term in the diff-in-diff, the average f-1 to f-1 plus L outcome evolution in the treatment group, we are just going to use the sample variance of those f-1 to f-1 plus L outcome evolution. And we're going to similarly compute the variance of the f-1 to f-1 plus L outcome evolutions in the control group. And finally, our estimator of the variance of beta at L is just going to be the variance of the long differences in the treatment group divided by the number of treatment groups, plus the variance of the long differences in the control group divided by the number of control groups. And you can show that actually this is an unbiased, it's not unbiased, sorry, it's a conservative estimator for the variance, for this variance here. And this estimator becomes not conservative, it becomes exact if treatment effects are actually homogeneous. But if treatment effects are heterogeneous, this variance estimator could overestimate the true variance. But because we have this bias in frequency statistics towards making sure we don't make type 1 error and not worrying so much about type 2 error, in that conceptual framework, then having a conservative variance estimator is not too bad because all that you care about is not making too many type 1 errors. So then we can also show that this and it's just because the beta at FEL is just the difference between two averages of variables that are independent across groups. So you can apply the central limit theorem to the first average. You can to the average for the treated groups, and then you can apply the central limit theorem to the average for the control groups. And then you get a central limit theorem for the event steady estimator, which is stated here. And then using the variance estimator that we just saw, we're gonna be able to construct conservative confidence intervals for ATTL, and our confidence interval will just be of the classical form, estimator plus minus a critical value times, which typically would be 196, if we want to get a 95% confidence interval, times a standard error estimator. Actually, here I'm realizing there is a typo. Okay, so now the last thing I want to say on the, but here you see, sorry, so here you see that it's an asymptotic approximation, so it's a confidence interval that relies on an asymptotic approximation where we assume that both J0 and G1 tend to infinity, okay? And so an adjustment that's going to improve the behavior, that's going to improve the coverage rate of those confidence intervals when G0 and G1 are actually not that large, is that instead of using critical values from a normal distribution, so in my example, instead of using 196 as the critical value to construct the 95% confidence interval, Bell and McCaffrey have suggested to instead use the quantiles of a T distribution whose degrees of freedom is K, whose formula is here, and you see that K only depends on the number of control and treated groups. Okay, and Imbens and Colessar have shown that this modification can yield confidence intervals that will have better coverage rates in small samples. Unfortunately, the corresponding, you don't need to compute those critical values and the corresponding p-values, etc. by hand. They can be obtained automatically within Stata with this syntax here and with the R command dfadjust s. So then we conduct, so the natural question is, when are G0 and G1 large enough to rely on the confidence intervals that I've just described, okay? And we've conducted an extensive simulation study, which I am not going to detail, but based on this simulation study, I'd like to make 3 recommendations. So the first one is that we agree with Imbens and Colessar that researchers should almost automatically use the so-called HC2 standard errors with the DEF adjustment that was recommended by Bell and McCaffrey. The only case where maybe they don't want to do that is if G0 and G1 are really very large, because in that case, using those HC2 standard errors with the DOF adjustment of Bell and McCaffrey will not make a very large difference at all. And surprisingly, because when you understand what the adjustment consists in, it would seem like the computational cost of implementing those adjustments should be negligible. But yet, actually, in our Moser and Vuela application, where the sample size is fairly large, we have thousands of control groups and a few hundreds of treated groups. There, actually, the implementing the HC2 standard errors with the degree of freedom adjustment takes a little bit of time in Stata, and is not going to make any difference to the results. So, like if you have, let's say, more than a couple hundred treated and control groups, you can ignore this recommendation. But below that, I think it's very good practice to implement. So then our second recommendation, which is a recommendation based on simulations. It's not a theorem. I'm sure you can devise, very adversarial DGPs where this recommendation would break down. But based on our simulations, it seems reasonable to say that when both G0 and G1 are larger than 40, then you can use those HC2 and Bell-McCaffrey confidence intervals that I just described without running simulations based on your own data to assess the coverage rate of those confidence intervals. So in that case, you don't need to make sure that the asymptotic approximation underlying those confidence intervals applies to your specific data set, given the number of treated and control groups in your data set. So why do we think that in that case you don't need to run your own simulations? Well, it's just that running your own simulations is costly, and we've actually run extensive simulations where we've considered fairly adversarial DGPs, and even in those fairly adversarial DGPs, we always find that a 95% confidence interval based on these formulas always has at least 90% coverage whenever G0 and G1 are larger than 40. Okay, so it seems that even in pretty bad DGPs, when your G0 and your G1 are larger than 40, those confidence intervals are going to perform reasonably well. Now, what our simulations show is that when G0 or G1 are lower than 40, things become more complicated. Because on the one hand, you can find very adversarial DGPs where those confidence intervals are going to have bad coverage. But at the same time, you can also have DGPs, and one of the DGPs that we have is actually a DGP based on a real data set, on the Moser and Buena data set. So it's not an unrealistic DGP because it's the data in an actual paper published in the AER, where even with G0 or G1 much lower than 40, with G0 or G1 that could be as low as 5 or 10, those confidence intervals still perform very well. So when you enter the G0 or G1 lower than 40 world, it's just that you don't know. Because in some cases, in some DGPs, those confidence intervals could be really bad, but in less adversarial DGPs, they could perform very well, even with very small sample size. And so that's where we recommend that in that case, before trying to implement alternative confidence intervals that have been designed specifically for the cases where G0 and G1 can be very low, and we are not going to review those methods together, but they are not that easy. They are not completely straightforward to implement, and they rely also they have to rely on strong assumptions, of course, because, if you don't rely on an asymptotic approximation, then you need to make other assumptions. So there are costs attached to moving to those alternative estimation methods. So before moving to those estimation methods, to those alternative confidence intervals, what we recommend is to run simulations tailored to your own data. And to do that, you can follow exactly the example of what we do when we conduct simulations based on the data from Moser and Buena and adapt that to your specific setting. Okay, because those simulations, they might reveal that your data is a very adversarial data where those confidence intervals have bad coverage, and then you have no choice but start reading this section of the textbook where we explain what people can do when those confidence intervals are unreliable. But on the other end, those simulations might be very reassuring. They might show that despite your G0 and your G1 being pretty small, your data seems to be pretty smooth, well behaved, such that those confidence intervals have reasonably good coverage. Okay, and so that's a bit, and here, so in this section of the textbook that we are not going to review together, and which is pretty long and a bit more technical, we review one by one all the methods that have been proposed in the literature to conduct reliable inference when non-asymptotic reliable inference, when G0 or G1 are small. And, that includes some methods that you're probably familiar with, the Conley and Tabor method, but also some other newer methods. Okay, so maybe now is a good time to take some of the questions that were in the chat.
So I think we have two questions, one from me and one from Matteo. So the last two that you have received. Then there were other questions, but you already kind of answered.
Okay, let me see. Because last time it was very easy for me to access them, but now I don't see them. Would you mind resending them in the chat, actually?
Sure. So. One is sent.
Okay, no, but actually,
sent. I sent them all. You should find the bottom.
Yeah, okay.
Chat,
so the second one, that's exactly what we're going to be talking about now. So the one about, quantifying pre-trend deviations rather than testing the null that there is no pre-trend. And it's a very good question. But this one, I'm going to defer the answer. The first one, okay, so maybe I have to, I think I have to stop sharing my screen to be able to see them yet. So let me do that and I'll share again. Okay, so what are the treated control groups determining G0 and G1 in this setting where everybody gets treated at the same time? Okay, so this is very related this is very related to what we discussed last time about what is it that we define as a group and at which level do we make the independence assumption. So here I'm making implicitly in this, for instance, in this Moser and Buena application, when I'm saying I have 300 treated groups and several thousand control groups, I am making the independence assumption at the subclass level. Okay, I have 7,000 patenting subclasses, and I'm making the independence assumption at that level. And therefore, I have 300 treated subclasses and 7,000 or something control subclasses. So, and therefore, I don't need to worry about G0 or G1 being small. Of course, if I were to say, I don't know exactly how this classification into patenting classes work, but let's say that the classification with 6,000 units is at the 6-digit level. There is a classification at the 3-digit level where now we have only 50 patenting subclasses, and of those 50, 10 are treated and 40 are untreated. Okay, so if now you're going to say, okay, yeah, but I think that 6-digit patenting subclasses are correlated within the 3-digit groups, okay? And therefore, I want to make my independence assumption only between the 3-digit classes, but not within these classes. Then, if those are the assumptions you're willing to make, then now you're in trouble to rely on asymptotic arguments to justify to draw inferences. And what we believe is that one thing we push for in this in the book is that it's not a necessity to so here actually because typically researchers say, okay, I want to make the treatment at the level where I want to cluster standard errors at the level at which the treatment is assigned. Well, here it's not very clear actually how the treatment was assigned. Was it assigned individually at each subclass level, or was it assigned globally at the level of those 300 treated subclasses? We don't really know how that happened. But beyond that, we think that assuming independence at the very granular level, like I'm doing here, does not necessarily rule out common shocks that would affect several subclasses, provided those shocks don't lead to a violation of the parallel trend assumption. And here, when we look at the event study graph that we looked at together before, it seems that there is no common shocks that lead to a violation of parallel trend. Okay, so then Jeremy's question, does it matter which pre-trend coefficients are significant? Yes. Okay. So very good point. And that's something that has not received a lot of attention as well. That perhaps we should worry more about pre-trends, in the couple of periods prior to treatment than in 12 periods before treatment. But here actually it's related to the to the simple rule of thumb I was suggesting, in the sense that you can almost proceed. I don't know about the statistical properties of the procedure I'm about to describe, but you could almost proceed iteratively where you say, okay, let me test for pre-trends for one period. I don't reject. Then I have the right to show one event steady effect. Now, let me check if I actually have parallel trends for 2 periods. Okay. And then if I have, then I'm allowed to show one more event steady effect. Okay. And you keep showing event steady effects just so long as you don't reject pre-trends. And I think that this procedure would incorporate the very intuitive remark that Jeremy was making in the chat, that you should worry more about pre-trends just before treatment than about pre-trends many periods prior to treatment. Yeah, exactly. But I think so. The connection with the perspective of McKinnon and etc. I think it's a bit what I replied to Andrea. If you want further clarification on that point, you can talk about that in person. Okay. So now another very important topic, which are all the limitations of pre-trends tests. So first, very important limitation, which I think is obvious, but perhaps because it's obvious, it's not discussed, and because it's not discussed, people forget about it at the end, which is that the non-anticipation and parallel trend assumption, they are partly testable, not fully testable, in the sense that we can test for parallel trends before, but not after the treatment. And you might find that the treated and the control groups were on parallel trends before treatment, but you don't know if they would have kept being on parallel trends after the treatment. And because of that, parallel trends are suggestive. Yeah, they are not definitive evidence in favor of the validity of a Diff-in-diff design. And there is one paper that discusses, one very interesting paper that discusses a bit this issue, which is this paper by Canlong and Long. And what they say is that even when those tests are not rejected, then researchers should make perhaps more qualitative argument, because it's no longer going to be possible to make a quantitative statistical argument, but a more qualitative argument to assess whether it's likely that at the time of treatment or just after treatment, there was another event that might have led to differential trends, even if the treatment had not taken place. Okay, for instance, you need to reassure the reader that there was not like, if your outcome is, let's say, unemployment rate at the county level, you want to reassure the reader that there was not an economic recession at the time of treatment that would have affected that might have affected differentially the treated and the control counties, which could have led to differential trends. Because those events, if the recession takes place after the treatment, well, your tests for parallel trends, they will not pick up those differential trends because the recession was not there prior to treatment. Okay, so your tests of pre-trends are going to be blind to this type of phenomena, while this type of phenomena could arise and they could bias your estimator of the treatment effect. So one way, but at this stage, it's a very preliminary idea, which actually Canlong and Long also propose a similar suggestive way of testing a bit more quantitatively whether this type of concerns are plausible or not, would be to essentially identify observables, covariates, on which the treated and the controls differ, and check if those variables on which the treated and the control differ, whether or not they significantly predict the post-treatment outcome trends of the controls, while at the same time not predicting the outcome trends of the controls prior to treatment. Because, if you have an X that's such that the treated, let's say, have a higher value of X than the control, and then you see that in the control group, having a higher value of X significantly predicts your trend after the treatment, but not before the treatment, then that X might lead to differential trends between the treated and the control after the treatment, but not before the treatment. And, that's the type of things that would be a concern for a Diff-in-diff analysis. And, at this stage, it's a very preliminary idea. We've not really tried to formalize the assumptions under which it works. And of course, but, it's very obvious that it can be, it's going to be, again, a nice suggestive test, but it's not going to give you a definitive answer, because if you have differential trends that are not mediated by those covariates you're looking at, well, this test will not be able to detect that. But we think it's a potentially interesting avenue for future research. And another concern, so like in terms of the qualitative discussion that people can have about to try to support a bit their Diff-in-diff. A common concern is that treatments are rarely implemented in isolation. And so there is actually a nice paper. So in chapter 6, the empirical applications will be unilateral divorce laws. Okay, so we're going to talk about that in details. But this paper actually shows that in the US, unilateral divorce laws were typically adopted at the same time as other treatments, and in particular as legalizing abortion. And then, so there the concern is a little bit different. It's not that our event study estimators are actually just picking up differential trends. They are not picking up any treatment effect. Then in this type of situations, the concern is rather that our event study effects are picking up some treatment effect, but not the effect of the treatment that we believe we're estimating. We believe that we're estimating the effect of unilateral divorce laws, while in reality, we are estimating the combined effect of unilateral divorce laws and legalizing abortion. Okay? And this type of settings where you study a policy without realizing that the policy you're interested in is actually implemented at the same time as other related policies that can also affect the outcome you're looking at, we believe that they are not so infrequent. So, like there again, having like a more qualitative section of the paper about the historical context, trying to convince the reader that there were not other policies implemented at the same time, that there was not another concomitant shock that would have differentially affected the treated and the control. We think those are good practices that should become much more part of the standard Diff-in-diff paper. Okay, so that's the first important limitation of pre-trends test, that they can test for. We can test for pre-trends before, but not after treatment. The second concern is that pre-trends tests often lack power. Okay, and this concern has been the reality of this concern has been demonstrated by Roth 2022, which systematically evaluates the power of parallel trends test in 12 papers published in like some of economics top journals like the American Economic Review, American Economic Journal Applied, and Economic Policy. And he conducted an exhaustive search of the papers published in those journals from 2014 to 18, looking at papers that would contain the phrase event study and whose data was publicly available, and that estimated an event study regression. And so for each paper, he collected the vector of event study coefficients and their variance covariance matrix, and then he ran the following simulation. So in each draw of the simulation, for each paper, is going to generate some fake event study coefficients from a normal distribution with variance covariance matrix, the one in the paper, and an expectation having this formula here for some real number lambda that's gamma that's different from 0. So in the DGP, in those simulations, do we have that the parallel trends assumption hold? And what is the value of ATTL? So if the parallel trend assumption holds, what should be the expectation of those event study coefficients when L is negative? Yeah, exactly. It should be 0. Is it equal to 0 here? No, because even so, this term will not be here for negative L's, but this term will be here. Okay? So that's a DGP where we have differential linear trends. And gamma represents the differential linear trend between the treated and the controls. Because forgetting for now about this term, this represents the differential counterfactual outcome evolution in the two groups if the treated had not been treated. And you see that the longer the horizon, the bigger the trend difference becomes because, like the two groups are following their own group-specific trends. Okay? And then the treatment effect corresponds to this term, which is just the actual estimated effect in this studies. Okay, so the DGP really perfectly mimics the data in those studies because you see the coefficients are drawn from a normal distribution with the same variance covariance matrix as in the paper, with the same estimated treatment effects. The only thing that's manipulated by Roth in his simulations is that he assumes that we have differential trends and he's going to calibrate on that. Okay, so then in each simulation draw, Roth is going to say that a test of pre-trends is rejected whenever he draws at least one pre-trend coefficient that's significant at the 5% level, namely that the drawn coefficient is greater in absolute value than 196 times its standard error. So Roth is well aware of the fact that this is not a valid test for pre-trends, that instead you should run an F-test, but in practice, in those 12 papers he revisited, so actually it's a bit of an aside, but it's quite interesting. So so all of those papers show event study graphs with pre-trend coefficient on the left with their confidence intervals and event study effects on the right. So talking to Roth, there are actually many papers that don't do anything with the pre-trend coefficient. They just don't comment on them. Okay. Then you have a few papers which is already better than the more sophisticated than that first group of papers that run this type of pre-trends test. Okay, we'd say, okay, is it the case that I have at least one pre-trend coefficient that's significantly different from 0 or not? And based on that, they decide whether the parallel trend assumption is rejected or not. But then the number of papers that do the correct thing, which is to run an F-test, is really actually a minority of those 12 papers. And those are not all papers. So you see the methodological sophistication of researchers when it comes to Diff-in-diff estimation has really been increasing a lot recently, because nowadays it seems pretty obvious to us that we should be running an F-test. And even not that very long ago, that's not at all what people were doing. Anyway, so that I'm closing the aside. So Roth fixes some values of gamma, and for each value of gamma is going to run the simulation, let's say 1,000 times, and is going to compute the percentage of times that he rejects the null of parallel trends, which here is the correct thing to do because we know that we have differential trends. So that means that for each value of lambda, of gamma, is evaluating the power of his test for 3 trends. And he's going to evaluate power across a range of values of gamma until he finds the value that we're going to denote gamma 0.5, such that the test of 3 trends is rejected 50% of the time. Okay, so gamma 0.5 represents the differential trend, the linear differential trend between the treated and the control that would have exactly 50% chances of being detected by the analyst given their variance-covariance matrix of their coefficients. And finally, is going to evaluate this quantity here and compare it to that quantity here. So what is the purpose of that comparison? Yeah, exactly. Yeah. So the interpretation of this term is that it's the bias in a study's estimated average treatment effect on the treated that could be generated by a differential linear trend that the researcher would only have 50% chances of detecting. So it's really a very, very nice and clever summary measure of the power of the pre-trends test. Okay? And then we're going to compare that to the actual estimator of the ATT. And when we take the ratio of this divided by that, that's telling us what is the percentage of what we think is a treatment effect that could actually just be what is a bias coming from differential linear trends that we had 50%, which is not zero, but very, very far from 100% chances of detecting. And now the bad news is that what is bad news is in this figure. So this figure shows the blue squares on this figure are the actual estimated ATTs in those 12 papers reviewed by Roth, and the green circles are those what is So the green circles are those terms here. Okay, so they represent the amount of bias that could be generated by differential linear trends with 50% chances of detection, while those blue squares are the ATTs. And you can see that, there are papers that are doing well, like for instance, in this paper, Well, the differential linear trends would account for a bias of around 1, but the estimated ATT is 6. So the potential bias would actually not change all that much our estimated ATT. That paper is also doing well. Yeah, as well. You see, like the potential bias is very low actually in comparison with the estimated effects. Same thing for that one. So you have some papers for which this is not too much of a concern, but you have other papers like this one where almost all of the estimated effect could actually be generated by differential trends. Okay. And when you aggregate across the 12 papers and you take, you could choose other threshold, but let's say that we start worrying when differential linear trends could account for at least a half of the estimated effect, then there are 7 out of the 12 papers, so more than half, where differential linear trends could account for at least 50% of the estimated effect. Okay, so maybe we are actually, I'm going to skip this green question here, directly showing you the result. So the goal of this question was to use the pre-trends command programmed by Roth, which gives you this gamma 0.5 number that runs simulations based on your own data to determine this gamma 0.5 number, this differential linear trend that you would have only 50% chances of detecting. The issue is that this command is a bit slow. And in fact, I was never able to, in the Moser and the Buena data, I could never make it work with 18 pre-trends estimator. I had to stop at 6 because otherwise it would really take too long to run. But this figure shows the results. So here you see I'm only showing the 6 pre-trends estimator on the left that I'm using to calibrate the differential linear trend that would have 50% chances of being detected. And then this differential linear trend is extrapolated all the way to the right into the post-treatment period. And you see that actually all the short-run treatment effects can be almost fully accounted for by differential linear trends that we could fail to detect. While on the other hand, the very long-run treatment effects, they cannot. They are too large to actually just come from such differential linear trends. Okay, and we're going to skip that. So maybe before we move on to the next section, maybe we can take a 5 minutes break and then we'll resume at we can resume at 3:50, let's say. What is? Okay, perfect. See you in 5 minutes. Okay, so we've seen one we've seen one estimator of the event study effect ATTL, but that's unbiased under the no anticipation and parallel trends assumption. But actually, there are other possible unbiased estimators, and one can show that, for instance, this beta hat BLGL estimator is also unbiased. And
we don't see your screen. We see a black screen at the moment.
Okay.
It's written you're sharing, but we just see something black. Yeah, perfect. Thanks.
Okay, good. So the Yeah, so when we're going to study binary and staggered designs with variation in treatment timing, we will discuss estimators proposed by of the ATTL effect proposed by those 3 papers. And actually, if we have no variation in treatment timing, the estimator proposed by those 3 papers just reduce us to that expression here. Okay, and that's because those papers are by Borosiak, Liu, and Gardner. That's why I superscript this estimator by BLG. So could you explain the difference, going back to the formula for beta at FEL, could you explain the difference between beta at BLGL and beta at FEL? Yeah, exactly. So the 2 estimators are Diff-in-diff estimators that compare outcome evolutions between the treated groups and the control groups from a pre to a post period. The difference is that beta at FEL only uses the last period before treatment as the pre-treatment period, while this estimator uses an average of all pre-treatment periods as the baseline measure of the situation before treatment. Okay? But, under parallel trends assumption, we have that parallel trends holds between any pair of consecutive periods. Therefore, it holds over any horizon, and therefore, without treatment, the average outcome evolution from, here we can think of this as being an outcome at period f minus 1 plus 1 divided by 2, because, it's the average of all those pre-treatment periods. So under parallel trends, we also have parallel trends from f divided by 2 to f minus 1 plus L, and therefore, this is an unbiased estimator of the effect of L periods of exposure. So this estimator, so the standard estimator, we've seen that it can be obtained from an event study regression where the omitted time period is f minus 1, the period just before treatment. And that's why the regression uses period minus 1 as the baseline in the Diff-in-diff. So with that in mind, how could we set up an event study regression that would give us, as sum of the coefficients, those beta at BLGL estimators? Yeah, exactly. So we would omit all the pre-treatment periods, and that's the regression that's written here. Okay. So you see the two are very similar. It's just that in one case, we have all periods except for f minus 1. The other one, we have only have periods after the treatment. Yeah, exactly. We could also estimate it, quote unquote, manually. But here I was trying to, find like a way we, as researchers, we often like to use regressions to compute estimators. because they are convenient, and then they allow us to do like testing on the coefficients, etc. So it's always convenient to have a regression formulation of an estimator. Now, another way of computing this estimator. So here, we're at this stage, we're just seeing three numerically equivalent way of computing the estimator. The first one is, like Matteo just said, we just compute this Diff-in-diff by hand. The second one, like Andrea said, is we run this regression. And now there is a third way, which is an imputation procedure. So it's a two-step procedure where in the first step, we restrict the sample to the untreated cells. And in that subsample, we run a two-way fixed effects regression of YGT on group and time fixed effects. And of course, because nobody is treated in that subsample, we don't have, a coefficient for the treatment. We just have the group and the time fixed effects. And then we use the regression to predict or to impute the counterfactual outcome of the treated GT cells. Okay, so we take for each GT cell that's treated, we impute its missing untreated outcome as the sum of the fixed effect of group G estimated in that first step regression plus the fixed effect of period T estimated also in that two-way fixed effects regression. And then it's possible to show that the beta BLGL estimator is numerically equivalent to just the sample average across all the treated groups of their outcome, their actual outcome L periods after treatment minus their predicted outcome L periods after treatment if they had remained untreated. Okay, so now we have three numerically equivalent ways of computing this new estimator. Now the question is, we're going to try to compare the properties of this estimator to the properties of the classical event study estimator. So when we have two unbiased estimators of the same target parameter, ATTL here, typically we want to use the estimator whose variance is the lowest. Okay. So intuitively, which of the two estimators will have the lowest variance? Yeah, exactly. So a very natural intuition is to think that this one here will have the lowest variance. And the intuition, which is an intuition coming from it's a cross-sectional econometrics intuition that using more data can never harm. We're going to see that under some assumptions, this intuition is true, but because actually here, the data we are aggregating is not cross-sectional data, G is fixed here, we are averaging across T, so we are actually in a time series world, and then there's going to be assumptions under the serial correlation of this time series, under which actually the intuition breaks down, and where actually this estimator has a higher variance than the standard one. Okay, so to formalize things a little bit, remember that under our parallel trend assumption, the never treated outcome follows a two-way fixed effect model. Its expectation follows a two-way fixed effect model, and therefore, by letting epsilon GT be the difference between the outcome and its expectation, we have that the outcome is the sum of an alpha G fixed effect, a gamma T fixed effect, and the error epsilon GT, which is mean zero by construction. So Borosiak et al. Show that if the treatment effects are non-stochastic, so the only stochastic component of the model are those epsilon GT residuals, errors, and if the epsilon GT residual are independent and identically distributed, IID, across both G and T, then this beta hat BLGL estimator is the best linear unbiased estimator, the blue, of ATTL. And because this estimator here is also a linear unbiased estimator, then we must have that the variance of the BLGL estimator is lower than the variance of the event study estimator. Now, a concern with that result is that it relies on fairly strong assumptions, namely that we have that the errors are independent. Across G, that part is fine. That's an assumption that most papers in this literature maintain, and that we are also making in this book. But the result also assumes that we have independence across T. And that's a very strong assumption that most of the literature is not making. It's trying to avoid making, actually, by using, for instance, standard errors clustered at the group level. Now, in some sense, like when you want to have, variance estimators, variances are typically complicated objects that don't have very simple closed form expressions. So when you want to have this type of results where you can have neat comparisons between sharp inequalities between the variance of one and the other estimator, you most often need to make simplifying assumptions. So at this stage, it's not necessarily shocking that this assumption needs to be made to compare the variances. But the question then becomes, how sensitive is this inequality to this assumption that we have no serial correlation in the errors? And unfortunately, there is a very recent paper by Harmon, 2022, who shows that actually this inequality is very sensitive to this assumption, because if instead of assuming no serial correlation, you make kind of an opposite polar assumption that actually errors are very strongly serially correlated in the sense that they follow a random walk or an IR1 with a unit root. Epsilon GT is equal to epsilon GT minus 1 plus an idiosyncratic shock UGT. Then that means that errors are not independent, but on the contrary, they are very strongly serially correlated. Then Harmon shows that in that case, it's actually the standard event study estimator that's the blue. And that then implies that the estimator of Borosiak, Liu, Gardner actually has a larger variance than the standard event study estimator. So now to convince ourselves, because many of us have been educated at a time when we were not necessarily receiving as much time series classes as we should, this type of counterintuitive result that using more data can be harmful might be a bit shocking. So let's try to get a bit more intuition. So let's assume that we have 3 time periods. Then we can only estimate one event study effect. And we've assumed that treatment effects are non-stochastic. Therefore, only the untreated outcomes are stochastic. And then this beta at 1 BLG estimator is going to be comparing the average outcome evolutions from an average between Y1 and Y2 and Y3 in the treatment and in the control groups. Okay? And therefore, the stochastic component, the stochastic part of this estimator will just be averages of these variables. Okay? YG3 without treatment minus an average of YG2 and YG1 without treatment. Now we can plug in this decomposition for the untreated outcome. The alpha G fixed effects are netted out because we are looking at the same G at different time periods. And then we have, so these terms are not going to matter because they are non-stochastic. Those are the period-specific fixed effects. And then we have the error at period 3 minus the average of the errors at period 1 and 2. And now I plug into this equation my random walk assumption. And finally, thanks to that assumption, you can show that this simplifies to the error at period 3 plus a half of the error at period 2. Now, let's do the same exercise, but for the classical event study estimator. That estimator is simpler. It's just going to average differences between Y3 and Y2. And therefore, the stochastic part will just have this expression. And here you see that the variance of this will be lower than the variance of that. So here, if we have very persistent stochastic shocks, averaging more pre-treatment periods is not helpful. It's actually just adding more and more noise to the estimator. Okay, so now how to discriminate between estimators by comparing their variance? Well, here it's not really helping because there are not totally implausible DGPs where IID, where one estimator dominates the other, but other not totally implausible DGPs where this is the opposite. And in real life, we're probably somewhere in between IID and random walk. So we don't really know which one is going to be better. So then another thing we can do is sensitivity analysis. Okay. Of course, both under the no anticipation and parallel trends assumption, the two estimators are unbiased, but we are in the context of non-randomized natural experiments where the no anticipation and parallel trends are not things that are going to be true by construction. Those are strong assumptions. And of course, we can run pre-trend tests, but we've just seen that pre-trend tests may not be as powerful as we would wish them to be. And then it becomes important to assess the sensitivity of the two estimators to violations of those assumptions. So if we have that the parallel trend assumption does not hold exactly, and the differential trends get larger when we start comparing the treated and the control groups over longer horizons, then this estimator is going to be more biased than the classical estimator. And the reason is very simple. It's just that it's using all the pre-treatment periods, and therefore it's comparing the outcome evolutions of the treated and control from F over 2, averaging all the pre-treatment periods, to F minus 1 plus L, which is a longer horizon than the F minus 1 to F minus 1 plus L used by this estimator here. Okay, so if we have differential trends that get bigger and bigger over time, this estimator will be more biased than this one. On the other hand, so that means that there is a bit this idea that this estimator is less robust to violations of the parallel trend assumption. Now the issue is that when we have two assumptions underlying those two estimators, we also have the no anticipation assumptions. And here it's a bit the opposite. There is this idea that if we have anticipation effects that arise just before the treatment, then those anticipation effects are going to bias a lot this estimator here, which puts all the weight on period F-1, the one just before the treatment, while those anticipation effects will be a bit more diluted for that estimator because it uses all the pre-treatment periods. Now, I would argue that there are many cases where violations of this assumption are more of a concern than violations of this assumption. And those are the cases where there is a clear date when the treatment was announced, such that you can immunize both of these estimators against anticipation effects by redefining the treatment date as the date when the treatment was announced. And so in that case, we don't need to worry so much about violations of the no anticipation assumption. And while violations of the parallel trend assumption remain a concern, and then that would lead us to favor this estimator here. So overall, our recommendation is rather to use this estimator, but keeping in mind that this should not be a crucial choice. The choice between these two estimators should not be a crucial choice that would dramatically change the results of your study. Why is that? Well, that's because if your identifying assumptions are valid or approximately valid, the two estimators should actually be pretty close because they are both under no anticipation and parallel trends. The two estimators are actually unbiased for the same target parameter. So if this choice between those two estimators is actually a critical choice because, you know, one of them is significant and positive and the other one is significant and negative, that actually means that you should stop your study because you have clear violations of parallel trends and no anticipation that invalidate both estimators, actually. And to exemplify the fact that using one or the other estimator should not really be a crucial choice, at least in some context, here we are going to estimate the estimator of Borosiak, Liu, Gardner by just running the same event study regression, but we drop all the pre-trends. And then we put those on an event study graph. And when we do that, you see that the two are extremely close. Okay. So there was a question, I think, on the chat. Let me look at it. Okay, interesting point. Yes. Yeah. But typically you would see that using some kind of pre-trends test. You would see that, you know, in the period just before treatment, you have some kind of Aschenfelter's dip, exactly like you say. And Yeah. So that would then, But then when you have this type of phenomena, unless you're ready to assume that the Ashenfelter dip is only affecting the period just before treatment, otherwise it becomes a little bit hard to do estimation. Okay, so now we're going to see methods to estimate heterogeneous treatment effects. And we're mostly going to be concerned with estimating the correlation between the effects and some covariates. Okay, to see. So let's assume that we want to assess if the effects of L periods of exposure are correlated with a vector of time invariant covariates xj, where xjk is going to denote the case coordinate of xj. And we assume that we have a constant in the vector. So for instance, let's say that we run analysis at the level of municipalities in Chile, and we want to assess if effects vary with the poverty rate or the share of the population that has a college degree in the commune. So then our target parameter is going to be this beta Lx quantity, which is the coefficient on the covariates xg in a regression that's, of course, infeasible because you don't observe those variables, but that you can at least theoretically think of, an infeasible regression of the effects on xg. And then you could use those coefficients to do prediction, to predict the treatment effect of a given location by computing x prime g times beta x. And that's often referred to as the best linear predictor of the treatment effects given the covariance. Now, if if the dimension of xj is 2 and xj only contains one non-constant variable, then the coefficient on the non-constant covariate is just the covariance between the covariate and the treatment effect divided by the variance of the covariate. And if actually the non-constant covariate is binary, then our best linear predictor coefficient is just the difference between the average effect of the treated groups that have a value of the covariate equal to 1 minus the average effect for the treated groups that whose covariate is equal to 0. So if k is equal to 2 and xj2 is binary, then estimating this best linear predictor coefficient is very simple. We can just run again our two-way fixed effect event study regression, but we do it separately among, let's say, the groups with an income level above the median and the municipalities with an income level below the median. And then we will take the difference between the event study coefficients in the two regressions. Instead of, estimating running this estimation in 3 steps, estimating one event study regression, another one, and then taking the difference between the two, we can actually do this in just 1 step by running one two-way fixed effect, one event study regression, where we interact the covariate with the treatment, the time fixed effects, and the relative time indicators, and then the coefficients on the relative time to treatment indicators interacted with xg2 will be numerically equivalent to the difference between the event study coefficients estimated in the two subsamples. So this estimator is unbiased for the difference between the average treatment effects in the two groups under the following assumption. So this assumption says that among, in my example, among municipalities above the median income, the average counterfactual outcome evolution is the same between the treated and the control groups. So this is what we sometimes call a conditional parallel trend assumption. We require that within the municipalities above the median income, we have parallel trends between the treated and the control group, and we also have parallel trends within municipalities with an income below the median. So this type of strategy to estimate heterogeneous treatment effects, they are very easy to implement when we want to investigate heterogeneous effects alongside a single binary covariate. They can be extended to the case where we want to investigate heterogeneous effects alongside covariates that take a small number of values relative to the sample size. So let's say, for instance, that you have a sample size with 5,000 municipalities, and you want to investigate heterogeneous effects alongside two covariates. One is quintiles of income per capita, and the other one is whether the municipality is above or below median for the percentage of college graduates. That gives you two covariates that can take 5 times 10 times 2 is equal to 10 values. And you have 5,000 municipalities. In that case, it's realistic to extend that estimation strategy by just estimating your two-way fixed effects regression separately in the 10 subgroups, or equivalently, running one single regression where you interact everything with dummies for each of the possible value the covariate can take. Okay. Now, this type of strategy is not going to be applicable when XV actually takes a large number of values, when you want to estimate treatment effect heterogeneity alongside covariates that take a very large number of values. And this is going to be the case, especially when some of the coordinates of XV are actually continuously distributed variables. So in that case, we're going to review an extremely simple estimator that actually, until recently, has been proposed only recently, and actually has been proposed, I think, for the first time in this textbook. That relies, on perhaps a strong assumption, but that can be placebo tested. So when we have, covariates that take a large number of values, and we might have a vector of many covariates, what we can do to estimate the beta LX coefficient is to use this estimator here, which is just the coefficient on the covariates in a regression of the long difference YG f-1 plus L minus YG f-1 on the covariates, restricting the sample to the treated groups. So what is the identifying assumption underlying this estimator? Well, we're going to denote by beta delta y0 Lx, the coefficient in a regression of the counterfactual evolutions without treatment on the covariates among the treated groups. And so the identifying assumption underlying this estimator, yeah, exactly. You're following very closely the literature, Matteo. And up, you see. So so the identifying assumption underlying this strategy is that those coefficients should be zero, meaning that among treated groups, the counterfactual evolutions without treatment should not be correlated with the covariance. And that's something that you can test by with some kind of pre-trans test by regressing treated groups outcome evolutions prior to treatment on the covariates to see whether or not this assumption is plausible. And another interesting thing about this estimator is that to compute it, you see that you don't need to have control groups, actually. You can compute it even if all the groups are treated, which shows that under this identifying assumption, your control groups are not necessary to estimate the correlation between treatment effects and some covariates, which, as Matteo was pointing out, that's a result that was actually first noted by this paper by Shan 2023 and in this textbook. And now, so to compare this estimator with what people are doing in practice, well, people sometimes, when they just have a binary covariate, people sometimes just, separately estimate the regression in the two subgroups. But when their covariate is not binary, what they typically do is that they interact the treatment with the non-binary and potentially continuous covariates that they're interested in. And there are a few special cases where doing so leads to an estimator that's numerically equivalent to the estimator we just reviewed, meaning that those two-way fixed effect or even study regression with an interaction term yield an unbiased estimator under some kind of parallel trend assumption. But there are actually many cases where those regressions with those two-way fixed effects with interaction terms are not numerically equivalent to the estimator we just described. And then we are actually not aware of any paper that has studied what those coefficients from two-way fixed effects with an interaction term estimate under a parallel trend assumption. And it might very, given all that we now know about two-way fixed effects regressions, it might very well be that when we start studying a bit precisely those coefficients, we're going to have bad surprises and realize that they don't at all estimate what we would hope them to estimate. So, which is why we at this stage recommend estimating this type of very simple regressions of long differences on the covariates, restricting attention to the treatment. Okay. So yeah, we're gonna stop here for today. We are almost done with this third chapter. What we will do when I come to LISER next week will be to cover the last topic in this chapter on the classical designs, which is about limited dependent variables. When we have a binary outcome, how can we do Diff-in-diff with a probit or a logit model, that type of things. Is there any question before we stop?
I think we had one from David. You can see it in the common chat.
Yep. Okay, so wouldn't the fact of estimating No, very good point. So exactly. So we know that we now know that two-way fixed effects regression are not robust to heterogeneous treatment effects, and adding interaction terms between the treatment and some covariates in the regression is not going to solve the problem unless your model for the heterogeneous treatment effects is correctly specified that treatment effects only vary alongside the covariate you're including, but that let's say treatment effects are heterogeneous between the counties above and below median income, but within those two groups you don't have any effect heterogeneity. And this, surprisingly, even though there's not been a ton of research on that, the last results I was mentioning suggest that this may actually even be true in classical designs without variation in treatment timing, binary and absorbing treatment, etc. Because in those designs, the baseline, issues with baseline two-way fixed effects regression only start appearing in more complicated designs where the treatment could be non-binary or you have variation in treatment timing, etc. But those more complicated regressions where you interact the treatment with a covariate, it seems that they can be non-robust to heterogeneous effects, even in the classical design where the treatment is binary, absorbing, etc., which is why in that case, we recommend using an heterogeneity robust method like the one I've just described. Okay, very good. So see you next week in person then.